Okay. Good afternoon, everybody. My name is David Litchfield. I'm the Managing Director of NGS Software, although my other title is Chief Research Scientist, and in that capacity I'm here today talking to you about Oracle backdoors, otherwise known as rootkits. The reason I've very recently been looking at rootkits again is because I'm moving more into forensics, database forensics these days, and I'm interested in trying to work out whether there are any things that can be done to help detect for things like backdoors, and eventually get to the point where you increase the technology to the point where these things almost become undetectable. And one of the examples we'll be looking at today is an in-memory backdoor that essentially changes some data, specifically the password hash for the system user, such that anybody can then log on, provided they know what the new password is going to be. So it's essentially because you're not hooking any kind of function or changing any code in memory, and you're changing data that is there to be changed, it's going to be very difficult to protect against, basically. So database backdoors or rootkits are really nothing new. In 2001, NGS Software, the company I work for, warned of a potential backdoor in SQL Server that basically you change the X status of one of the user accounts and you could still log on. So it essentially looked like this was a group user, a group, but essentially it turned out to be a user who could log on with full privileges and so on. Chris Anley then moved further on into database backdoors. He wrote a paper called Violating Database Enforced Security Mechanisms, and essentially it covers runtime patching. It essentially hooks there's a function called f has object permissions that basically looks up the UID of the user, and if that user ID returned is 1, then no permissions checking is done. So the actual compare is patched essentially, so it always returns the effective user ID as 1, so that permissions checking is essentially disabled. And then in 2002, a couple of days later in 2002 actually, as part of the paper that I presented at Black Hat, that eventually had the code in it to exploit the SQL Server name resolution service that eventually was exploited by the Slammer worm. In there I also spoke about Trojaning extended store procedures and start procedures and everything like that. Then Database Hacker's Handbook that myself and a couple of other colleagues wrote at NGS Software. We warned about the dangers of trusting views when doing audits of database servers, simply because views can't be trusted. Most recently, Alexander Kornbrast has been speaking about hiding users and processes, and then last year at Black Hat in Oracle Rootkits 2, he brought up an interesting, of his talk, the most interesting topic there, I believe, was pin procedures. What pin procedures basically means is essentially you can lock in the Oracle SGA the code of some PL SQL packages, basically. So you can manipulate, modify the package, lock it in the SGA, and then change the code back again, so that if anyone comes along and does an audit of the procedure, like for example, compares the checksums, then the original checksum is there, but the one in memory is actually the one that takes precedence. So that was an interesting attack. The problem is current rootkits are trivial to spot. So I'm asking the question here, if we've got all this stuff on database rootkits, what's the point in having a talk today, nearly 5 years after the topic was originally broached? Why continue talking about database rootkits? Well, current rootkits are trivial to spot. We've solved that problem. We can, find these things really easily. What about the next generation of rootkits? And indeed, in Alexander's talk last year, he alludes to third generation toolkits that basically, modify data and so on to allow access. Now, Alex's talk didn't really present any third generation rootkits. So today, that's what I'm going to present today. Basically, is present a couple of third-generation rootkits that demonstrate what can be done. So before getting to that, let's look at some of the current backdoors or rootkits. I mean, some people might break into a database server and create themselves an account which they can then come back to and log into later on. Now, obviously, anybody doing an audit of the server will come along and select from, say, for example, DBA users and see this account called hacker or whatever it happens to be. The point is a DBA who is on the ball will recognize that there are accounts on the system that really shouldn't be there. So the next step to that is basically, hiding, modifying the view such as DBA users and all users, so that when someone comes along and does a select username from DBA users, the account name is essentially hidden. Other methods of backdooring, Oracle. Oh, well, actually, before we talk any further, this isn't just applicable to Oracle, by the way. This is across the board as far as all database servers are concerned, or in terms of the ramifications. But in terms of the specifics, obviously, we're dealing with Oracle here. So modify some PL SQL packages. Trivial to do, especially if you have an unwrapper. There are a couple of unwrappers floating out there, but essentially you unwrap the code, make your modifications, and rewrap the code and upload it again. Now, obviously, trivial to spot again because the checksum of the PL SQL package has changed itself. Other ones there are some dangerous PL SQL packages that, for example, take a string and executes that string as straight SQL. Now, a lot of the sysown packages will do that. I list a number of them in the Oracle Hackers Handbook. The idea is basically if you lose access for whatever reason, then or you lose your DBA privs if you've given yourself DBA privs, you can go around giving yourself these privs again by executing one of these PL SQL packages. Modify or create after logon triggers, so every time someone logs in, you can check whether the user has the requisite permissions. If they do, you can go and do execute some nefarious code. And again, the same with startup procedures, or indeed going all the way to modifying binaries. Now, we'll look at a couple of examples of these and why they're, in terms of implementation, so, well, not poor, but easy to spot, and how they go about themselves. So, modifying views, along comes a user, creates himself an account called hacker, and he wants to hide the fact, so they'll modify the view of DBA users and all users so that the hacker account isn't displayed. Because it's modifying an object in the data dictionary, this is trivial to spot. One of the aspects of this is checksumming the code of the view and then comparing that later on is not the right way around, to check for modifications. Because at the end of the day, you're trusting a database server which may have been compromised. So it's, if the attacker's, that advanced, basically, they can modify the database server such that when someone does a check on the code of the view, for example, they might use the dbMess utility package to create the checksum, then they just need to modify that and fire back whatever they want you to see, essentially. So essentially, you need to go to the data file itself, extract the view body from that, and do your checksumming on that directly. Another way of not worrying about the views problem is essentially just use the underlying table itself. Rather than relying on DBA users, just use the sys.user table and so on. Now, a very nice, simple way of checking whether someone's actually manipulated the DBA user's view, for example, is using the minus operator. So I'm just going to change the view for a second here, so that an account called Hagsaw is not shown. If we see there in the bottom right-hand corner, essentially we're modifying the view there so that if the user hacker is displayed, is there, don't show it, essentially. So if I actually go ahead and create that user first, connect/ssdba, create user, Hagsaw, identified by password. grant create session to Hacksaw. Okay, so if we do a select username from DBA users, username equals Hacksaw, we can see the user exists. So we modify the view essentially so that, now obviously this requires the requisite permissions, but we can do this through, for example, PL SQL injection vulnerability. There's a number of them. So the next time we run that query, no user exists. So the thing is, if we compare those two, if we select from users where type is 1, in other words, a user, and we select from username where from DBA users, if there's any rows returned, then that says there's a difference between the underlying view and the underlying table and the overlying view. So that indicates that there is indeed a problem with DBA users. So that's been changed. So that's just using the minus operator. We, of course, when we're doing an audit, rather than using DBA users and having to worry about that, just use the underlying table essentially. So if I just change that all back again. Okay, so if we then go back and redo this, there should be no difference between the two. So no row selected, so that's good. So our hacker account should exist again. So select username from DBA users, order by 1. So there we go. So it's visible again. That's good. Okay. Okay. So you get the idea. These are trivial to spot. We just check some of the code of the view, or just use the underlying table essentially. So rather than actually modifying the view itself, another way of achieving the same thing actually is exploit the view contents instead. Now, what do I mean by that? Well, if we look at the text of the view, there's a whole bunch of predicates down here. Oops, excuse me. These are the predicates here, essentially the where clause. So if we get rid of that. Now, all we need to do is essentially pick one of these things and make it not true, and ensure that we can still log in with that account. So for example, if we look at this row here, where u.dataTS number is the same as dts.ts number. That's essentially looking at the default table space and everything like that. Well, if we choose a table space that doesn't exist, this DTS, by the way, is anyone, do we have a laser pointer, by the way? No? Okay, it's not worries. I'll just highlight it here. This DTS here is essentially taken from there. So if we modify the user directly, so he has a data.ts. Oh, great! Thanks very much. Remind me to give it to you back at the end of time. How does this work? So essentially, in here, if we choose a table space number that doesn't actually exist, and we'll do this. So here we're going to set the data TS in the user table to 1337. One row updated, commit that. If we select username from DBA users, where username equals Hacksaw. No rows are selected essentially, and that's because here, when that view is essentially called,